Had we had a spacecraft that could have taken a single close-up picture of Oumuamua, it would have really resolved many of these controversies. So I think the big message is science is exciting, space is exciting, and this is the area for exciting careers for the young.
The object we're discussing today was first detected in 2017. Maybe you can walk us through a bit of the story. I remember when we spoke way back then, you kind of hinted at learning about the true value of adrenaline.
We have the Pan-STARRS telescopes that are funded by NASA to survey the night sky to look for potentially hazardous objects, things that come near the Earth. And it just happened, I'd been working really hard. I'd just come back from a scientific meeting. I hadn't had a day off for a couple of months. And so finally I had Sunday off, and Richard Wainscoat, who was the PI on the NASA funded program, called me at home and said, "I think we found an interstellar object." And my first thought, I didn't tell this to Richard, was, did it have to be today? This was my first day off. But in fact, I got really excited. And what had happened was Rob Werk, who is working with Pan-STARRS, had seen it in the data stream on the morning of the 19th of October. And it looked like a rapidly moving object. And like many of the near-Earth objects, they look backwards in the data to see if they can find data on previous nights and get a preliminary orbit. And they did find it on the 18th, but 2 nights isn't enough to really say much. That gives you a straight line. But by the 22nd, with more data from Mauna Kea using the Canada-France-Hawaii telescope, they were convinced it had a hyperbolic orbit, meaning it wasn't from our solar system. So that's when Richard called me. And that's when the adrenaline spiked up, because I realized my day off was over and we were going to have to scramble and secure telescope time on telescopes all around the world. And if we could have the first slide, this just shows what the Pan-STARRS telescope looks like on Maui. And the facility scans the sky every night when it's clear, obviously, and looks for moving objects. There's now 2 of these telescopes. So that led to a huge campaign to characterize it, but we only had about a week to do it before it got really too faint for the main science. The orbit was what really caught our attention at first, but the second thing is we started to observe it is, we had long predicted that these sort of objects would be entering our solar system, but the predictions expected that the very first one would be a comet. Typical comets are small bodies left over from the formation of the solar system made of ice and dust. And when they get close to the sun, the ice warms up, pushes the dust off, and gives us a tail. And that makes it easier to see. It gets brighter. So we thought the first one would be a comet, and this didn't look like a comet. The orbit had brought it really close to the sun, inside the orbit of Mercury, and it was outbound. It was on its way out. It had already passed the Earth when it was discovered. So it was surprising it didn't have a comet tail. We also looked at its brightness as a function of time, and the variation was huge. Again, a little bit atypical of solar system bodies. And then the most unusual thing that I'm sure we're going to talk about later is that it wasn't just behaving controlled by the gravity of the planets. It was actually accelerating away from the sun.
Let's talk a little bit about the name and how that name came about and its significance.
Yeah, this was the first of its kind, and you really want to think carefully about the first of its kind whenever you discover something. And we thought, in honor of it being discovered in Hawaii by astronomers at the University of Hawaii, we should have a Hawaiian name. So Doug Simons actually suggested that we contact some native Hawaiian experts in linguistics at the Imaloa Center and gave them 2 days to suggest a name to us. And so they came up with the name Scout or ʻOumuamua, which means scout or messenger sent from our distant past to reach out to us.
I remember that early on in that first year, you were very focused on what exactly might the composition of ʻOumuamua be. Can you talk a little bit about that?
Yeah, the way we go after composition is through spectroscopy. In other words, we're trying to measure the amount of reflected light at different colors. And different chemicals will absorb different wavelengths of light. And so that can give you a fingerprint or a map of what's on the surface. Unfortunately, we couldn't get a proper spectrum in great detail on ʻOumuamua because it was too faint. We didn't have much time, but we were able to measure different colors on the surface. And it was red. And that means it reflects more red light than it does blue light. It doesn't mean that it's going to be a bright red color. And in fact, in slide 9, we have some examples of what red means for solar system objects. And in the bottom images on the lower left, this is just a black and white image of the Rosetta spacecraft target 67P Churyumov-Gerasimenko. This is black and white. But the picture next to it shows the picture in true color. And that is a red comet surface. So that reflects more red light than blue. And the reason for this is that it's organic rich. On the other hand, the thing right next to it, the two panels to the right of it in the bottom, this is Saturn's moon Iapetus, and the front side is red. The back side is white looking and it's icy. And the reason for the strange dichotomy on this one is because it's moving around orbit and it's collecting dusty debris on the surface. And this one is not red because of organic compounds. It's red because it's got a lot of iron minerals on the surface. Now, the top two figures on the left shows an actual color image of ʻOumuamua that looks slightly reddish. And then the one on the right is just black and white from HST. The point is, it's red. That makes it look like a comet, but beyond that, we cannot tell you what it's made of. Could either be iron-rich compounds, or it could be like a comet with organics. And that's all the data we will ever have, so I can't tell you any more about its composition, except that I don't think it's titanium spacecraft hull.
So let's talk about the origin or the possible origin of the object. Anything you'd like to say about that?
Well, yeah, let's start with slide 2, which shows a graphic that shows the trajectory through the solar system so people can get a feel. And starting on the left path, you can see it approached from above the plane of the solar system, whipped around past the sun, and then went outbound. And in the inset, you can see that it really did come close to the sun inside the orbit of Mercury. So it would have been quite well heated. And then you can see the little dot on the outbound leg, which shows the point at which we discovered it. It had already passed Earth. So it came from the direction of the constellation Lyra, the bright star Vega. And people were excited because we know that there's some young planetary systems there that are just forming. And so the idea is that what you want to do is try and get such precise positional data that you can trace its path backwards in time. So thanks on the slide. And so we took really detailed measurements. And the problem is, while we have an excellent orbit of ʻOumuamua, you can't just rely on its orbit because all the galaxies and the stars in the galaxies are moving. And so as we're tracing its path backwards in time, we have to know where the stars were backwards in time. And so it was fortunate in 2018 that the Gaia telescope survey, whose duty was to measure precise positions and velocity of stars, did a huge data release. And so one of our team members actually did the calculation of moving 7 million stars backwards in time to where they would have been to try and trace ʻOumuamua's path. And what we're trying to do, did you pass close enough to any young star system that you could have been kicked out of that young star system? And the answer was there were 4 systems that it might have been close enough to, but there was a problem. It was going too fast. And the normal process, and in fact, if you could bring up slide number 3, we have a picture of what a young solar system might look like. And in this picture, you see in the right foreground, a giant planet, Jupiter, a Jupiter-like giant planet, because this is an artist's impression. If one of these tiny little planetesimals comes too close, it can give it a kick and throw it out, but it doesn't have enough energy to throw it out really fast. So thanks on that. The problem with ʻOumuamua was, while we found 4 candidate systems where it passed close enough, the velocities were way too high. So we knew they weren't right. And so in fact, while we did our best, probably this experiment is pointless, because unless this was recently ejected nearby, there's no chance you're ever going to know the star positions well enough to do this experiment.
The Harvard astronomer Avi Loeb has really wanted the world to take seriously an alternative hypothesis, let's call it that ʻOumuamua could be, or could have been, an alien space probe. I know that most astronomers disagree, but maybe you can give us some points, some arguments on both sides of that proposition.
I can only give you some arguments on the side that I disagree that this is an alien spacecraft. Yeah, I think it's great to actually ask the question. And I really wish what he would have done was engaged the public in a conversation of what would it take to convince us that this is alien technology. And in fact, there were a couple of experiments that were done with ʻOumuamua to test that. And I know reporters had asked me, isn't that silly? And I said, no, why wouldn't you do the science? And so what they did, there was the Square Kilometre Array in Australia that in November looked at ʻOumuamua at radio wavelengths. And then again, the Breakthrough Initiative used the Very Large Radio Telescope in early December, I believe, to also listen for signals. Neither of them detected anything. And the Green Bank telescope was extremely sensitive, and they could have picked up a signal equivalent to, say, our Dawn spacecraft in the asteroid belt. So whatever this was, it wasn't broadcasting radio signals, but you have to do the experiment. You know, why wouldn't you? That's a cheap and easy experiment to do. And in fact, it was useful for science because that placed some limits on water outgassing in the radio also. However, what he's claiming is because we didn't see gas, that it therefore has to be this solar radiation principle of, you know, the sunlight pushing gently on what he called a solar sail, because this is a technology that we're thinking of for spacecraft propulsion. You don't require any fuel. It's just a thin, very thin sheet. And so he estimated that you'd need something less than 1 millimeter thick. But it's still, we already knew its size from its reflectivity. So the thing that I find fundamentally wrong and he didn't address was, how do you get a light curve that has a ratio of 10:1 when you're going from something really large, 100 meters, down to millimeters? That's not 10:1. Furthermore, it was tumbling, like a wobbling top. And for solar radiation, anyone who's a sailor knows a tumbling motion is not a good thing to do when you're trying to sail in the wind. So my problem was he did not address all of the science. He picked parts of the science that fit his hypothesis. And I don't think that's a good way to do science. The question is appropriate to ask because that's the way you discover new things.
So if you had had the ability, and if we had had the forewarning, would that have been top of your list to send up an intercept?
So I think the way to go in the future is to have a spacecraft ready to go, something that's either already built and on the ground that you can launch, or something in orbit that's sitting there waiting for something. The in orbit sitting there is not as desirable because it will get damaged due to the radiation environment over time, or if you have fuel on board, run out of fuel. And on the other hand, if you launch from Earth, you have a lot more thrust, so you can get to many more places. But the Europeans are actually experimenting with this with the Comet Interceptor mission, which will be sitting out in space for a few years waiting. They're waiting for a long period comet. They're hoping for an interstellar object, but I think the chances that they're going to get one at the right time is very small. So I think we need a new style of missions from NASA, one that's all ready and you just launch it immediately. And also because no matter what, we're not going to have a rendezvous where you can sit and stay at the object. It's too much energy. So it's going to be a fast flyby. And so I think the best way to do this is with a miniature fleet of spacecraft, CubeSat style, that are attached to a mothership. And of course, UH is developing these small sats. So I think we have the opportunity for getting in on some of this nice technology. And what you can do with that, NASA is very conservative. You don't want to have a hugely expensive spacecraft get too close to an object, and that limits what you can do. But you could launch the CubeSats from the mothership to get close and assume the risk and then transmit the data to the mothership. So I think that's going to be the new style of mission if we want to study one of these.
You're hinting at suggesting that Earth is not necessarily utterly unique in hosting life. It's your belief that there likely is life elsewhere.
Oh, absolutely. As I looked it up because I wanted to see how many exoplanets today, and as of today, we've got more than 4,400 known exoplanets, with about 7,400 more candidates that are likely to pan out as exoplanets. And among those, there's over 3,000 planetary systems. And within those, many of those planets are actually in the habitable zone, which is the special distance from the sun where liquid water could exist on the surface of a world if it had an atmosphere. And we have seen throughout the history of Earth that life started very early, almost as early as the Earth was cool enough to have oceans. And it will probably persist far into the future, but of that whole period of time, it's mostly microbial throughout that whole history. So I think it'll be a very narrow slice of time that has even macroscopic life, plants and animals, and an even smaller slice with technology. So I think there's absolutely life out there, but I think the most likely life that we might detect first will be microbial life, and hopefully within our solar system.